Hello. Today we're going to take a look at topic 6.9. We're going to integrate with a method called substitution. So this is kind of like the inverse of chain rule. And we use it typically when we have products, or mainly I'm looking for composition functions, right? So I'm going to write that up here. Composition functions. All right, so when I have composition function, a function within a function, within my integral, I'm looking to use substitution. Okay, so if you can see here, I have a composition of functions. I have 3x minus 4 substituted into x to the fifth. So what I'm going to do is I'm going to let that be u. And off to the side here, I'm going to write let u equal 3x minus 4. Okay, and now follow the process here. I'm going to take the derivative of u. So I'm going to say du equals 3 dx. Now notice on the right-hand side I had an x, so if I take the derivative of 3, I kind of put a little dx next to it, kind of indicating my differential, the variable which I took the derivative of. And what I'm going to do is I'm going to solve for dx. I'm going to divide this 3 over to the other side, and I'm going to call this a 1/3 du. Now, watch what I do here, okay? Currently, our integral in red has a problem because we have the variable u, but we're trying to integrate with respect to x. That's a big problem, but I know dx is equal to 1/3 du. So the way that I write this is I'm going to say u to the fifth, and then instead of dx, I have a 1/3 du. I can take the 1/3 out front because it's just a constant multiplier. Oops, I wrote an x. Hang on, that should be a u. And now I can take the antiderivative. So I would get u to the sixth. Okay, I would get a 1/6 out front, and then don't forget about that 1/3 that was already there. So I have a 1/18 u to the sixth plus c. Now what I like to do is I like to then back substitute my u value, my expression for u back in. So I have a 1/8 u was a 3x minus 4 to the sixth power plus c. This is my antiderivative. Okay? So let's try to do this again. I'm going to change some colors here. So if you notice, I'm going to leave the 6x squared alone. And again, you can see my composition. I let my u equal the x to the third plus 4. So du is a 3x squared dx. I'm going to get that dx all by itself. Okay. And I am going to write my new function. So I have a 6x squared times u to the fifth, and instead of dx, I have a 1 over a negative 3x squared du. And if you look, some good things happen here. The x squareds cancel, and 6 times a negative 1/3 would end up being a negative 2. And I have u to the fifth du. So I can now integrate it, 1/6 u to the sixth plus c. And then I would write my final answer as a negative 2, a negative 1/3, because I want to multiply those together. So a negative 1/3, and then my u was an x cubed plus 4 to the sixth power plus c. Okay, and that would be my antiderivative. All right, let's try to do one more. So again, I want you to see this integral. Let's go back to my red and blue here. I have my composition on top. So I let u equal the square root of x plus 1. So that means du is going to be a 1 over 2 square root of x dx. And if I bring that over, I'd actually multiply 2 root x du equals dx. So I get something that looks like this. So now if I write my integral, I have u squared over the square root of x, and instead of dx, I have a 2 square root of x du. Now, again, nice things happen. The square root of x's cancel. I'm going to take the 2 out front, and now I can just integrate. So I have a 1/3 u cubed plus c, which would give me a 2/3 times my u, which is the square root of x plus 1 cubed plus c. And this would be my antiderivative. Okay. And I have more. So number 4. Again, I'm looking for my composition of functions. So here I have times e, and I'm going to make my cosine u, right? I have a function of a function. So I let u equal cosine of x, which means du is a negative sine of x dx. If I divide that over, I'm now going to substitute in for dx. Right? And the fun part, the signs cancel. If I take out a negative 1, and the antiderivative of e to the u is still e to the u plus c, of course. So I get a negative 1 e to the cosine of x plus c. This would be my final answer. Now, number 5 is tricky. Okay, number 5 has a few more elements into it. I want you to take a closer look. So you can see my composition of functions. So I'm going to say the cotangent of u. And in this case, we let u be 3x. So watch what I do here. Oops, sorry. Derivative of 3x is 3 dx. Divided over, I get a 1/3 du equals dx. So when I write this, I'm going to have a 1/3 times the integral of cotangent of u du. But the problem is I don't know what the antiderivative of cotangent is. I know what the derivative is, but that doesn't really help me. I need to know what the antiderivative is. So here's what I'm going to do. And this is where I want to show it to you because this is kind of hard to figure out on your own. So cotangent of u, cotangent is cosine of u over sine of u du. And I'm going to do a second substitution of, I'm going to let a different variable, w be sine of u. So then dw would be cosine of u du. And I have a 1 over cosine of u dw equals du. So now I'm going to have a 1/3 cosine of u over, we made the sine of w, times 1 over cosine of u dw. And you'll notice the, oops, let me erase that little piece there. The cosines cancel. And what I get, I'm going to write it off to the side here, is the integral, or 1/3 times the integral of 1 over w dw. So I get a 1/3 the natural log of w plus c. So now I'm going to put my w back in, which was sine of u plus c. And then I'm going to put my u back in, which was a 3x. Okay. All right. So these are our kind of special case problems. I want you to see them. So number 6, I kind of put a little header on it. It says u sub is used, but you must solve for x. I want to show you what I mean by that. I didn't have a better way to say it. So I'm going to do everything the same. I'm going to write this as the integral of x over the square root of u. And we let u equal x plus 1. So then du would be a 1 dx, or in this case, dx equals 1 du. If you divide, you still get 1. So if I do this, I can say x over the square root of u, and then dx times 1, or it's just going to become a 1 du. The 1 doesn't really make a difference. And I have the integral of x over the square root of u du. Now there's a problem here. I can't integrate this because, again, I have 2 different variables. Okay? So what I am going to do is, do you see this u equals x plus 1 at the top? If u is equal to x plus 1, well, I'm just going to subtract that 1. I'm going to solve it for x. So now I have the integral of u minus 1 over the square root of u du. I'm going to split that fraction up. And if I do that, I get u to the 1/2 minus u to the negative 1/2 du. So now I can integrate it. U to the 3/2, 2/3, right? Minus u to the positive 1/2 with the 2 out front, plus c. And then I'm going to plug my u back in. So I have a 2/3 x plus 1 to the 3/2 minus 2 times x plus 1 to the 1/2. I put 3/2. 1/2 plus c. So this would be my antiderivative of that function. Okay? So number 7 is also a special case. Okay, you can kind of see how it looks like a sine inverse, right? So I'm going to put it up here. Looks like sine inverse. Okay? However, there's that 4x squared on the inside. So here's what I'm going to do. I'm going to rewrite this. I want you to see this is very tricky. Instead of saying 4x squared, I'm going to say quantity 2x squared. That's still a 4x squared. So now you can see the composition. I'm going to let u equal 2x. du will be 2 dx. So I get a 1/2 du equals dx. So I now have the integral of 1 over the square root of 1 minus u squared times, instead of dx, I have a 1 over 2 du. So I have a 1/2 times the integral of 1 over square root of 1 minus u squared du, which will be a 1/2 sine inverse of u, and we know u is 2x. So I get a plus c at the end. That would be my antiderivative. Okay? So again, doing u substitution. Now, we can do u substitution with definite integrals too and get the area under the curve. Now, I want to show you 2 kind of different ways that we can do u substitution with definite integrals. You can choose whichever one you like the best. So the first way is I am going to do my u substitution. So let's start there. So you can see I'm going to do the integral from 0 to 2 of t squared, and then inside I'm going to make this u dt. So we let u equal a t cubed plus 1. So du equals 3t squared dt, or a 1 over 3t squared du equals dt. So let's write this better. From 0 to 2 of t squared, square root of u, 1 over 3t squared du. And then the t squareds cancel out. So now I have a 1/3 times the integral from 0 to 2 of u to the 1/2 power du, which is going to be a 1/3 times u to the 3/2, but then a 2/3 out front. And we said on definite integrals, we don't have to worry about the plus c. So we're just going to evaluate this from 0 to 2. However, the 0 and 2 are x values. So I'm going to back substitute that u back in. So t cubed plus 1 from 0 to 2. And if I plug 2 in, I'm going to call this 2/9. 1/3 times 2/3 is just 2/9. Times, if you plug 2 in, I get 9. Oops, this should be to the 3/2, right? So 9 to the 3/2 minus the lower limit, which would be 2/9 times 1 to the 3/2, which I would get 2/9 times 27 minus 2/9 times 1. And if we reduce this down, I get 6 minus 2/9, which I believe is 52/9. That's my answer. That would be the area under the curve. So we did our u substitution, right? We found the antiderivative, and then we got it all back in terms of t, so then we can evaluate it. Now, here's something I want to show you that AP does every so often. So for number 9, I'm going to do this slightly different. So I'm going to do my u substitution still. And I'm going to let that sine of x be my u. So u is equal to sine of x. So then du is cosine of x dx, or 1 over cosine of x du equals dx. So now watch what I do here. So I have 0, pi over 2, cosine of x times 1 over cosine of x, and these cancel. All right, now here's a problem. My integral right now has the only variable in it is u, but the limits are x's. So what they do sometimes, instead of saying x equals pi over 2, they might say, okay, well, u for that upper limit is going to be the sine of pi over 2, which is 1. So they'll write this integral with a 1 up here. And then, instead of x equaling 0, they'll say, well, u is sine of 0, and sine of 0 is 0. So I would go from 0 to 1 of the square root of u du. And then when I take my antiderivative, I'll get u to the 3/2, 2/3 out front, plus, I don't really need the plus c, habit, from 0 to 1. And I can just plug 1 and 0 into that, because those are now u values. So I'm going to plug 1 in, and then I'm going to plug 0 in, which that would end up just giving me 2/3 as my answer. So if you notice, I changed all of my limits so that they were also in terms of u, and then I substitute it accordingly. So you have the choice. Either you can get it all back in terms of, for number 8, we got it back all in terms of t, and then left our limits the same. Or you can just leave it in terms of u and change your limits to now like u values and then substitute those in. Okay? All right. There's a whole bunch of practice for you to take a look at. I want you to see what you can do. All right? And let me know if you have any questions on the next lesson.